Good morning, everyone. Good evening, everyone. This is Chaitanya Kumar from IIT Madras, and welcome to week 6 of Analog Circuits tutorial. In today's tutorial, we will cover some aspects of making filter design. So let's start. So we have studied the concept of active RC biquad. So we will try to build upon that. So what we will try is we will try to build the following transfer function E of S or H of S is equal to S square by omega naught square plus S by omega naught cube plus 1. Okay. So let's try to build this. So as we have seen previously that second order transfer functions can be built using active RC technique. So the technique we will see today is Thomas bipod. So what we have over here is so we have this R1, RC1. Let's have this as R. Then we have another op amp. So R2, this is C2, and we have this complete thing over here. This is R. Okay. So we have seen a similar thing. We used this kind of structure to have a band pass filter. So let's see whether the same structure can be used to implement this low pass filter or not. We'll try to compute the transfer function from input to output and then proceed from there. So in order to calculate transfer function, so we have V naught over here. Let's call this node as Vx1. Let's call the Vx and this node as Vy. Okay. So can you tell me what is the relationship between Vx and Vy? Vx is related by some k times Vy. Minus Vy. Correct. So this over here, as you can identify, this is this is an inverting amplifier with gain of 1. So Vy will be equal to minus R by R times Vy. Vx is equal to minus R by R times Vy, that is equal to minus Vy. Okay. So we know the relationship between Vx and Vy. Now, other thing, let's see what happens from the relationship between Vx and V naught. Can you tell me that as well? Sorry. Yeah, let me copy this structure on the next page as well. So since we know Vx is equal to minus Vy, so we can remove Vy and write here minus Vx itself. Okay. This is V naught. So we will write here as minus Vx only. So can anyone tell me what is V naught by Vx? So what structure is being implemented over here? Sorry? Integrator. So what is V naught by Vx?
minus 1 by
-1 by
R2
R2
integral
C2
integral dt
integral
dt.
dt. Okay, but what is it in terms of S domain? Since we are trying to calculate the transfer function, right? We are
Okay.
trying to. So what is it in terms of Laplace domain?
1 by s.
1 by S. Correct. So we now know this node is minus Vx, this node is Vx, this node is equal to V naught, and what V naught is equal to minus Vx times S C2 R2. Okay. So we know the relationship between all the internal nodes. Now let's see what, so let's try to calculate Vx, and if we are able to calculate Vx, we can calculate V naught as well, because we know the relationship. So let's try to apply KCL at this point. So what are the currents? Let's call this I1, this is I2, this is I3, and this is I4. So there are four currents that are going inside this node, and the KCL will be so KCL, let's call this node 2. KCL at node 2 will be I1 plus I2 plus I3 plus I4 is equal to 0. What is I1? I1 is Vi by R. What is I2? I2 is
Minus
minus
bx by r1.
minus Vx by R1. What is I3? I3 is
Minus s
minus
bx by s.
minus Vx by
1 by cs.
1 by Cs.
c1
So
c1
that will just be SC1 times Vx, right?
yes sir.
And then at last we have R4. R4 is basically V naught by R again. Okay, this is equal to 0. Some people have some questions. I will get back to the questions. So assignment 4, right? So Ravi, we will have this explanation of this question once, and once that is done, then I will allow you to share the screen to show the question, and then we can discuss that. Will that be okay with you? Okay. So okay, so Vx we have over here. Now here we knew that so V naught is equal to minus Vx by Sc2R2. Hence Vx is equal to minus Sc2R2 times V naught. So this, if we substitute in the KCL equation, we get the following. So here we have Vi by R minus So plus V naught we can take out common. So we will have SC2 R2 by R1 plus SC1 S square C1 R1 R2, sorry, S square C1 C2 times R2 plus 1 by R. Okay. It is clear till here, right? Is it correct? So SC2R2 minus SC2R2, and here it will be minus S square C1 times C2R2 plus 1 by R. Correct. So this is equal to 0. So Vi by R. So this R can be taken common. So the whole equation can be divided by R. So Vi plus V naught times SC2 R2 by R1 times R plus S square C1 C2 R2 times R plus 1 is equal to 0. Okay. That means V naught by Vi is equal to minus 1 by S square C1 C2 R2 R plus S C2 R2 R by R1 plus 1. So let's try to put this circuit over here again. Now this is the circuit over here, and what was the transfer function that we required? We required the following transfer function. Let's put this also over there. Now let's say I have R2 equal to R. Then what happens? We get minus 1 by S square C1 C2 R2 equal to R, and let's also say we have C1 equal to C2. Okay. So we get S square and let's call this as C. So we get S square R square C square plus S square just a minute. This is R1. R1 over here. Yeah, correct. Plus SC R square by R1 plus 1. So we want the equation to look in this form, right? So what we will need is 1 by R square C square is equal to 1 by, this is equal to omega naught square. Comparing the second order term of both of them, that means to say RC is equal to 1 by omega naught. And if RC is equal to 1 by omega naught, this term can be written as so this term over here can be written as minus 1 by S square by omega naught square plus So this can also be written as SCR times R, right? So this CR will be equal to 1 by omega naught. So we have S by omega naught R1 by R plus 1. Now what we want? We want S by omega naught times Q. So what we have over here, R1 is equal to Q times R. So if we redraw the circuit, what we get? We get R over here. This is grounded. So this was R1 and R1 becomes Q times R. This is C. Then we have this as R, R. This is R again. This is C. And this is also R. So this circuit, so we have decided the component values and we get this as the circuit that gives us an transfer function of -1 by. So if this is Vi over here and this is V naught over here, V naught is equal to Vi times S square by omega naught square plus S by omega naught Q plus 1. Okay. Now let's say we wanted uh, instead of so at V naught by Vi at S equal to 0 we get as 1, right? -1, or the magnitude is 1. Just a minute. Now let's say we wanted a gain from input to output. Let's say we wanted something as V naught by Vi is equal to some minus of A instead of 1.
Sir, your screen is not visible.
Uh, oh, sorry. Is it visible now?
Yes, sir.
Yeah. So let's say instead of a unity gain, we wanted some gain of 1. So how we will go about doing that? Let's try to figure out. So what is our DC gain? How do we get our DC gain? We get DC gain. At DC, what will happen? This will, so let's try to build the DC circuit of this thing. Okay, instead of that, let's follow a different approach. Let's take the circuit over here. So now let's assume by changing the component internal components value, we have somehow managed to get the gain of. So we want a gain of A over here, right? So we wanted something like A by S square by omega naught square plus S by omega naught Q plus 1. So let's say somehow the current that is flowing in this direction is some I. Okay. So whatever current that whatever current I is flowing, this will flow through this capacitor, right? Do you follow till this point? Okay, so some current I is flowing through this resistor, and the same current, since it can't go inside this, that will flow through this capacitor. Now, initially, when this capacitor is C, whatever this current is flowing, that current times this capacitor gives you this output voltage as minus 1 by S square omega naught square plus S by omega naught plus 1. So now, just a minute. Yeah. So now you know that this current times this capacitance gives you minus 1 by S square by omega naught square plus S by omega naught q plus 1. Now, if let's say I wanted, let's say this current was not supposed to change and I wanted a voltage that is A times this thing. So, since I know that this voltage is equal to 1 minus 1 by SC times I, and somehow I managed to keep this I constant, and I want to increase this voltage by a factor of A, what shall I do to the capacitance? So earlier, this minus SC by I was equal to minus 1 by S square by omega naught square plus S by omega naught q plus 1. What I want V naught to be minus of, I want a factor of A over here. I am saying I won't touch this current I. If I won't touch this current I, how can I like what can I do? I can just let's say I multiply both the sides by A. So what I get, minus A by SC times I is equal to minus of A upon S square by omega naught square plus S by omega naught q plus 1. Okay. So what I have over here, whatever I had over here as C, if I reduce it by a factor of A, I can get the output voltage as minus A by S square by omega naught square plus S by omega naught q plus 1. So we will have a factor of A over here. Okay. Now, since we said that we don't want to change this I, now if we leave the circuit as it is, the V naught, which was initially minus 1 by a square, minus 1 by the second order denominator, has now become minus A by the second order denominator. Due to that, the current that will be flowing in this direction will also increase by A times, and the same current will flow and somehow impact this current I. Okay, we don't want to meddle with that. So what do we need? We want that whatever current was flowing initially in this direction, the same current should flow now also. If we assure that, then this voltage, if the current that was flowing is still the same as the current that was flowing initially, then this current won't change. Whatever is coming from here won't change, and hence this I will also remain constant. So if this voltage is increased by a factor of A, uh, in order to keep the current flowing through this resistor same, what will I have to do? I will have to increase the this resistance also by a factor of A. Okay. So now, so earlier, let's say the current over here was minus 1 by R times S square by omega naught square plus S by omega naught q plus 1. So earlier it was minus 1 by R times this. Now, since the voltage has increased by A, the resistance also has increased by A. So the current still V by minus 1 by R times S square by omega naught square plus S by omega naught Q plus 1. And hence, since this current is same, this current is still VI by R. So whatever current is flowing in this direction will also remain unchanged, and hence this I will remain unchanged. Is it clear? Okay. I am claiming that this circuit over here, I will copy the circuit to the next page.
Sir, please explain. You have put that we don't
Yeah,
want to. We want a gain of A, so we
yeah,
have multiplied C with C by A, and to not to maintain the same current, we have multiplied R with A. Up to that I
yeah.
have followed, sir. After that, what will do, please?
Okay. So basically, if what I want the only this node voltage to increase by a factor of A, right? So that we have achieved, correct? And since all other currents and voltages are still the same, so know that all other transfer function would remain whatever they were previously. Okay, so let's verify this. So what I am claiming is that this circuit over here will give me V naught by Vi as minus of A upon S square by omega naught square plus S by omega naught Q plus 1. Let's try to calculate and see whether we get this value or not. So again, we will try to calculate the. We need to verify whether this transfer function is correct or not. Correct. So again, we will apply KCL at this node. So what we had earlier, I1, we have I1, this as I2, this as whatever we had, we will have. Okay. This has I4, this as I3, and this is as I2. Okay. If this is V naught, this node was, we called this node as Vx and this node as minus Vx. Correct? Yeah. If this was so, what is the relationship between V naught and Vx now? It's still the integrator, right? It's just that the capacitance is reduced by a factor of A. So what we will have
CSA minus CSA,
minus
CS
V naught by Vx. V naught by Vx will be 1 by S R C by A. Correct? So Vx is equal to minus SRC by A times V naught. Okay. So let's try to write the KCL at node 2. So KCL Vi by R plus. So here this is minus Vx, right? So we have, yeah, this is minus Vx. So we have over here as minus Vx by QR minus Vx times SC, this is I3, plus V naught by AR, since this is AR now, is equal to 0. Now Vx we can substitute from here, Vi by R minus SCR V naught by Q times AR. So this will become plus because here there is one minus, here there is one minus. Both will become plus S square R square S square R C square. So my voice is still audible, right?
Yes, sir.
Yeah. Minus S square R C square by A times V naught plus V naught by AR is equal to 0. I have written this equation correctly, right? Yeah. So from here, let's take out AR common. So what we will have here is VI R plus 1 by AR. V naught also can be taken out common. So we have 1 plus SCR by Q plus S square R square C square is equal to 0. And if we rearrange this, R can be removed. V naught by Vi is equal to minus of A upon S square R square C square. The screen is not visible, is it?
No, sir, it is visible. It is visible.
Okay, Naveen, I think you can change the layout. Maybe you might not, or you might try to rejoin Naveen. Then probably you can see the screen. Are you able to see that now? Okay, so what exactly you are seeing? Are you seeing? Okay, rejoin and try. So we have S square R square C square plus SCR by Q plus 1. And initially we told, right, RC is equal to 1 by omega naught. So V naught by Vi is equal to minus of A divided by S square by omega naught square plus S by omega naught Q plus 1. Okay, so whatever we assume the transfer function to be, the same transfer function is there. Now, let's try to see whether this Vx node is still whatever was there previously. So what was our Vx node previously? In this case, if V naught is equal to minus 1 by the second order denominator, our this node will be minus SRC divided by S square by omega naught square plus S by omega naught Q plus 1. Okay. So let's see the same transfer function we have over here also. So we have relationship between Vx and V naught over here. So if V naught is minus A times Vi times second divided by second order denominator, so Vx will be equal to minus of SRC by A times Vi. So we have minus SRC by A times A S square by omega naught square plus S by omega naught q plus 1. So we still have the same Vx. Correct? So we saw that just by changing two components intelligently, we were able to get the desired gain. Now let's try to let's see. So we saw that Vx is still minus SCR upon S square by omega naught square plus S by omega naught q plus 1. Okay. Let's say I wanted, so I will redraw this circuit over here again. So the gain at this node is right now. Let's try write the transfer function. Here the transfer function is minus SCR upon S square by omega naught square plus S by omega naught q plus 1. And here the transfer function is minus A upon S square by omega naught square plus S by omega naught q plus 1. Okay. So can you help me plot both the transfer functions? So what is the kind of filter that Vx is, and what is the kind of filter that V naught is? What will be Vx at low frequencies? Okay, let's start with V naught. What will be the value of V naught at very low frequencies?
Yes.
A, correct? So it will start from A, and then it will remain flat like this. After that, after this second order denominators effect start coming, it will fall like this. What will be the slope in Bode? Let's say we wanted to plot the Bode plot. What will be this slope? So with what is the order of the denominator?
Second order.
Yeah. So so how does the second order denominator falls? With what slope? In deep decibels per decade.
Minus 20 decibels per decade.
Minus 40 decibels per decade.
Yes. Yes.
This thing will fall. Okay. And what? Let's say this is omega naught. Okay. So what will be the value at omega naught? Let's try to calculate the value at omega naught. So we will replace S by j omega. So we get V naught as minus A times Vi. So Vi is 1, of course, minus omega square by omega naught square plus j omega by omega naught q plus 1, right? And at omega equal to omega naught, we have minus A divided by minus omega naught square by omega naught square plus j omega naught by omega naught q plus 1, and this will be equal to, so this is 1, minus 1 and 1 will be cancelled, and at the end you will get, and this will also get cancelled, so minus aq by j, and its magnitude will be equal to, magnitude of v naught will be equal to a times q. Okay, so this term over here is a times q. Now if q is less than 1, this will always remain lower. So this blue curve represents something where q is less than 1, and if let's say my q became greater than 1, so my curve will look something like this. So at very low frequencies, still it will be equal to A. At very high frequencies, only S square term will dominate, so Q doesn't matter. And only near omega equal to omega naught, we will see a peaking in the magnitude response. And since Q is greater than 1, so A times Q will be greater than K, so we will see a peaking like this. Is it clear? Is it clear so far?
Sir, uh, whenever q is greater than 1, there will be peaking. It is
Yeah, whenever Q is greater than 1, the magnitude response will look like the black curve.
okay.
Yeah. So you want, so as you have studied about Chebyshev filter, Butterworth filter, and all these things. When you implement this in analog form, you need second order transfer functions with various quality factors. So by adjusting this resistor over here, you can get whatever quality factor you want, and you can cascade multiple of these things to get whatever frequency response you need. Okay. So clear so far?
Clear.
Okay. Now let's try to plot Vx also. So
Sir,
what?
according to the quality factor value, we can
Yeah.
change that to a Chebyshev or Butterworth. Is it?
Correct, correct, correct. So whatever so let's say you wanted sixth order Butterworth. Okay. So sixth order Butterworth, you will need three this kind of biquads cascaded with each other. So Vi, then V naught, then you will have one more biquad at this output and another biquad. And whatever, so you can go to MATLAB, or you can calculate whatever quality factors are required for sixth order Butterworth, and in each biquad you can put those quality factor and get the filter output. How you are to arrange the quality factors and all those things take into consideration non-idealities of the circuit. You know about thermal noise.
Yes, yes, sir.
You know about thermal noise, right? Have you studied thermal noise in detail? How thermal noise acts in the circuit, how thermal noise behaves as it passes through a transfer function, all those things have you studied?
No, no,
Okay, so you will study this in further advanced level courses, that how these quality factors are adjusted, like which biquad should come first, which biquad should come later. All those things are practical design aspects which you will study as you go further in analog electronics.
no.
Now we have plotted V out. Let's try to plot Vx also. So what will be Vx at very low frequencies?
It will be zero.
0. Or in decibels, so let's say we are talking about decibel over here, 20 log 10 of A. So in decibel scale, it will be minus infinity, right? 0 is minus infinity, correct?
Mm,
So it will start like this. And at very low frequencies, there will both the second order S square term and S term can be neglected. And if both of them are neglected, what will happen is it will start increasing at 20 dB per decade, correct? So at very low frequencies, we have Vx is approximately equal to minus SCR, right? Because S square and S term can be neglected. Can you understand this?
Yes, 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 yes.
Yeah. So at what rate this will increase?
Minus 20 decibels per decade.
It will
Yes,
increase
yes,
at
yes,
20 decibel per
yes,
decade.
yes, yes, correct.
Okay. So it will start increasing like this. Now, what will be at a very high frequencies? What will happen?
The denominator will be high.
Denominator will be high. So how will Vx look? So this at high frequencies. Let me do it over here. So Vx for omega much greater than omega naught. How it will look? We had S SC minus SCR divided by S square by omega naught square plus S by omega naught Q plus 1, right? So only S square term will dominate at very high frequency. So it will be minus, and CR is 1 by omega naught, right? So we can write it like that. So it will only be minus 1 upon S by omega naught, correct? So this is equal to minus omega naught by S. Now, how will this, with what rate this will drop? This will have a first order roll off, right? What is first order roll off?
Minus 20 decibels per
Minus 20 decibels per decade. Now this blue curve was minus 40 decibel per decade. So so it will behave something like this, or it will be much smoother, and it will go something like this. So if this is minus 40 dB per decade, this one is minus 20 dB per decade. And what will be its value at omega naught? Let's try to calculate that as well. Its value at omega naught will be at j omega naught. What we will have? Vx at omega naught. So we have minus j omega naught by omega naught minus omega naught square by omega naught square plus j omega naught by omega naught q plus 1. So this is equal to minus of q, right? This minus 1 and 1 will cancel. This omega naught will cancel each other. This omega naught will cancel each other. And j will cancel each other. So what we are left is minus q. Is this clear?
decade.
Okay. So we can finally plot it like this. And this value is q. In magnitude response, this value is q. This is equal to 20 log 10 of q. Okay. So we see that, let's try to, we will redraw this curve down for a clear discussion. We'll remove this thing. So, what kind of transfer function, what kind of filter does Vx has? What kind of filtering does it do at node Vx?
Please repeat the question, sir.
So, you have studied the types of filter, right? Band pass, band
Yes.
low pass, band stop, band reject. So, so what is so this is node V naught. What is V naught?
That is V naught is a low pass filter.
V naught is low pass filter.
Low pass filter.
What is Vx?
Band pass.
Band pass filter. Okay, so in same circuit, so this is the circuit, right? We have R, this is QR, this is C, and this is again R, this is also R, this is R, and this is C by A, and there is a feedback of AR. So node Vx is band pass filtering, node Bx achieves band pass filtering, node V naught achieves low pass filtering. Correct? So in the same circuit, both kind of filter you get. Now, one thing you see, so we have achieved that, let's say we wanted the gain at the band pass filter also. Let's say this also we wanted the gain over here as A. So whatever the current gain is, we want this Vx to be gained up by Q by A. Sorry, A by Q. Okay. This much gain we need at this node. So currently, if currently our so Vx initial is minus S by omega naught divided by S square by omega naught square, we want this gained up by. Why do we want this gained up by A by Q? So that the peak over here comes becomes equal to A. Okay. So S square by omega naught square plus S by omega naught Q plus 1. Okay, now what is the V final we want? V final we want as minus A by Q S by omega naught divided by S square by omega naught square plus S by omega naught Q plus 1. So Vx final will have a gain of A at omega naught. That is the maximum gain. So what we need to do? We will apply the same principle that we applied while scaling the low pass node. So let's say some current. So there are two sources of current. Let's say the combined current going inside this particular impedance is I. Okay. Now if this current is not changed and I want this particular node to increase by A by Q, what do I need to do with the capacitance? What I need to do with the impedance? I should increase the impedance or reduce the impedance?
increase the impedance.
Increase the impedance because Vx is equal to I times the Z, and if I is not to be changed, then this Z has to increase. By how much I shall increase the impedance? So
V.
C will become Ca by Q, and R will become in order to increase sorry, C will become, in order to increase the impedance of C, I need to reduce the capacitance, right? So this will become CQ by A. Okay, and R will become QR times A by Q. So this becomes equal to AR. Is this clear?
Yes, sir.
Okay, and I want no other node of the circuit to be touched. Okay, so now this voltage has increased by A by Q. In order for whatever current flows out of this node, if I maintain that also constant, then all other nodes of the circuit won't be affected, right? So if this voltage has increased by A by Q, this impedance I will have to
Reduce.
reduce by A by Q.
Q.
So I will make Q by RA. So my final circuit will look something like this. So this is AR, this is CQ by A, this is QR by A. This is R, this is R, this is C by A, and this is R. So what I am claiming is this node is equal to minus of A by AS by omega naught Q divided by S square by omega naught square plus S by omega naught Q plus 1. And this node is minus of A divided by S square by omega naught square plus S by omega naught Q plus 1. Okay, so let's try to verify whether whatever we have claimed is correct or not. So we will again try to find the transfer function to verify whether this and this expression is correct. So again, let's forget about these two for now, and okay, so let's call this node as Vx, this node as V naught. What is relationship between V naught and Vx? V naught by Vx is equal to minus A by SRC, right? Now RC is equal to, what is RC? So
1
we
by
have, sorry,
1 by omega.
1 by omega naught. So this basically is equal to minus of A omega naught by S, correct? And if this node was Vy, so what is Vx by Vy? Okay, let's call this node as Vx and this node as Vy. So this is V naught by Vy. And what is Vx? What is Vy by Vx? This is equal to, so Vy by Vx is equal to what is based on this
minus R
particular
minus R by
minus R by
Q R by A.
QR by A, and that is equal to minus of A by Q. Correct? Okay, so there is a little mistake over here. If this node increased by a voltage of A by Q, the resistance also had to increase by A by Q so that the current from this remains the same, right? We actually reduced it. Okay. So instead of QR by A, this should have been AR by Q. Okay. AR by Q. So this is again AR by Q, and this is minus of Q by A. Okay. So what is V naught by Vx from this equation? These two equations we have minus of A omega naught by S times Q by A, and that is equal to omega naught Q by S. So minus of omega naught Q by X. So Vx is equal to minus of V naught S by omega naught Q. Okay. So again, we will write KCL at node 2. KCL at node 2. So we have Vi by R, and so all four currents we will write again. So we have Vi by R plus Vx by AR plus SCQ by A times Vx plus V naught by AR. Okay, there are two negatives. This will become plus actually, plus V naught by AR. This is equal to 0. Okay, so again V naught we can substitute from here. Sorry, Vx we can substitute from here. So we have Vi by R plus, let's take out V naught common. So this becomes S by omega naught Q AR plus SCQ by A times S by, just a minute. Yeah. Okay. So SC omega naught Q plus 1 by AR is equal to 0. Okay. There is some issue, I think, over here. Uh, just give me a minute. So we have SCQ by A times Vx, and this is Vx, and this is V naught by AR. And from here, we get RC is 1 by omega naught. Okay, so again, we will take out 1 by AR common from this. So what do we get over here? S by omega naught Q plus S square. So this Q and Q will be cancelled. RC by omega naught plus 1. This is equal to 0. Now again, RC is equal to 1 by omega naught. So we have Vi by V naught as minus A upon S square by omega naught square plus S by omega naught cube plus 1. And this is what we claimed this to be, right? Okay. And what is Vx? We calculated Vx as equal to V naught times S by omega naught cube. So this is V naught by Vi. So Vx by Vi is V naught times S by omega naught Q. So minus A times S by omega naught Q divided by S square by omega naught square plus S by omega naught Q plus 1. Okay. So both the claims that we made were correct. Okay, so this technique of so this whatever the technique we applied in order to scale the voltage at output node or the voltage at this band pass node is called dynamic range scaling. So it can be done at the output of any op amp. So how it works is as follows. So let's say in a very big network of with multiple op amps, you have an op amp which has an impedance Z over here. So let's call this ZF, and it loads some other impedance loaded. Let's call this ZL, and some current I is coming. I1 is coming into the virtual ground of this op amp, and some I2 current is leaving, and there is a very big circuit around it. Now let's say you want to scale this node V naught by a factor of A. So what you will do, you so this I1 will flow through this ZF. So you will increase this ZF by a factor of A. So and this is virtual ground. So this will become minus of I1 times A ZF. So this node has increased by a factor of A. Now you want whatever is flowing out of this also to remain constant. So you will increase this also by a factor of A. So this will become A times ZL. So if you do this in a particular circuit, you can increase the voltage at one particular node without changing the transfer function at any other node. This technique is called dynamic range scaling. Any doubt in this?
Sir, got it. Sir,
Yeah, tell me.
can we go to the circuit?
This circuit.
Nice. This one. The first block, which one is without that resistance R that is equivalent to a integrator muscle. First block,
This one. Yeah, correct.
integrator. Yes, is a integrator. But due
If
to
this
this addition of this resistance and other circuits, it is becoming band pass filter.
this has become band pass filter, correct?
Okay.
So earlier it was supposed to be like this, and due to this particular this complete feedback and this resistor, instead of like this, it becomes something like this. It basically falls at zero. So in block diagram, this can be looked as follows. So what we have is, so its equivalent block diagram we can make. So here is the block diagram. So basically what we have is, we have an integrator, okay? And if we, let's say, put some value alpha around this integrator into feedback. So if in this integrator was, let's say, S by omega naught, so what will be the output? 1 upon 1 plus loop gain, right? Sorry, loop gain upon 1 plus loop gain it will be, right? So we will have minus 1 by alpha times S by omega naught alpha divided by, sorry, this is integrator. So integrator is omega naught by S. Omega naught alpha by S divided by 1 plus omega naught alpha by S. And if we write it the other way, so it will be minus 1
Why
by
we have
alpha.
multiplied with minus 1 by alpha?
So it's basically loop gain upon 1 plus loop gain times the beta, 1 by beta.
Okay.
The standard feedback closed loop expression. You can see this, right? So, okay, let's call this beta only then. So the beta is the feedback factor and loop gain is forward loop gain divided by, multiplied by the feedback factor. So let's call this beta. So what we have, 1 upon 1 plus S by omega naught beta. So an integrator, if a negative feedback is introduced in an integrator, its transfer function from omega naught S becomes like something like this. So this is called damped integrator. And the same thing is happening over here. So earlier it was only if this C was there, then this would have been an integrator. Now since a resistance DC feedback has been introduced, it becomes a damped integrator. So what you have over here is something like this. So the block diagram looks like this. It's some A by S, some A1 by S. Let's say this is some other factor A2. Then you have an inversion. You have here there is an undamped integrator. So this is A3 by S. And then you have complete feedback as A4. Okay. So this circuit and this block diagram are equivalent. Now, what you can do is you can try to find the value of A1 to A4 in order to get the transfer function that you have from this particular circuit.
So what you have done in the block diagram, there are two feedbacks as well.
Yeah, two feedbacks. So here also there are two feedbacks, right? There is one feedback around this integrator and there is one feedback after this integrator from here. The same thing over here.
I thought that it is a practical integrator, like the first is
Sorry?
resistor, first block in the diagram which you have drawn initially.
Yeah, so you can try to find out the transfer function of this and find out A1, A2, A3, A4 such that this transfer function and this transfer function are the same.
Sir, can you show the initial diagram which you have?
Sorry? Yeah.
Here the first block is actually it is a we call it as a practical integrator method. First block.
See, there is not, the I won't call this a practical integrator. If it had been a practical integrator, this resistance would have been very large. But
Okay,
this is a controlled resistance. This is not the parasitic resistance.
okay, okay,
So, in a practical integrator, this resistance would have been an
okay.
uncontrolled
Great,
value.
great, great, great.
Yeah. Here also there will be some resistance, but that resistance will be very large and that can be neglected. Any other doubts?
Regarding the term which was used in sixth assignment,
So,
uh,
regarding the
sixth assignment.
sixth assignment. So, sixth assignment has been, the deadline has not reached yet, right?
No, no, no. I want the not the regarding the solution. Uh, they have used the word natural mode.
Can you share the screen so that I can more clearly answer the query?
Yes, sir. So I don't know how to share, sir. I will read out the question, sir.
Okay.
There is a fifth question. A third order high pass filter uh, has the transmission zeros at omega is equal to 0 and omega is equal to zero point 0.1 radians per second.
Okay.
Its natural modes are at s equals to 1 and s equals to 0, 0.5 plus or minus uh, zero point 0.8 j. The high frequency gain is unity. Find the transfer function. That natural modes is it similar to our poles? Sir? Is it another thing?
Natural mode.
No.
Uh,
They use the
I
word natural modes.
just a minute. I am also not sure. I have not heard this term. So let me check. Okay, I'll Google it.
It is fifth question.
Natural mode of. Yeah, so a natural frequency is basically it's not actually the pole. Can you type that question? Can you copy that question and type it in the chat window?
Sure, sure. Okay.
Wait, I'll try to.
That way I have posted in the chat.
A third order high pass filter has transmission zeros at this thing. Its natural mode at s equal to 1 and s equal to third order. Yeah, so okay, it is talking about a third order filter, right? And it's saying two complex poles and one. So yeah, I think this is poles only.
Okay, okay. Thank
Yeah, I'll confirm that once, but it's most probably the poles. Yeah.
you. Okay. There is some want some clarity about. Sir, I'm audible, sir.
Yeah, yeah, you are audible.
Regarding the transformation filter from one filter to another filter.
Okay.
That I have gone through the video lecture. So can you, with small example, can you explain that?
Uh, can you please repeat your question? Your voice is not very audible.
Is it now audible, sir?
Okay, yeah, tell me.
Ah, to transform one filter to another filter from low pass to high pass or low pass to band pass.
Yeah,
A transformation.
yeah.
Can you explain that one with a small, very small example? That,
Okay, so okay, we can take one example over here. For example, we have a low pass filter.
your screen is.
Just a minute. Uh, okay, so what we have over here is, let's consider this low pass filter 1 upon 1 plus s by omega naught. Okay. So this is a low pass filter. How this is a low pass filter? So if we replace s by j omega, we have 1 upon 1 plus j omega by omega naught. So at omega equal to 0, so let's call this h. The mod of h is equal to 1. At omega equal to infinity, the mod of h is equal to 0. So this is 1 by omega, roughly 1 by omega, and omega naught by omega, and this is equal to 0. Okay. So let's say we want to transform it to a high pass filter. So what does transforming to a high pass filter means? So whatever was happening at omega equal to 0 should now happen at omega equal to infinity and vice versa. Correct? So
one second,
we,
1 second, sir. Sir, is it omega naught or omega, sir? Omega equals to 0.
oh, sorry, this is omega.
Uh-huh.
Yeah.
Okay, thank you.
Yeah. So whatever happens at omega equal, so these two have to interchange. Now, if this has to interchange, we shall replace s by 1 by s. Correct?
Yes,
Okay. So if we replace it that way, and since we want this to remain dimensionally correct, so it was s by omega naught. So we will replace s by omega naught by s. Okay. So that this thing still remains dimensionally correct. So if we do that, we have H high pass as equal to 1 upon 1 plus omega naught by S. So this S by omega naught is replaced by omega naught by S. Now if we have this, we have S upon S by omega naught divided by S by omega naught plus 1. Okay. Now again, if we have S as j omega in this equation, and this is j omega by omega naught plus 1. At omega equal to 0, we have H high pass as 0. At omega tending to infinity, so this 1 can be neglected, and we have H of high pass as equal to j omega by omega naught divided by j omega by omega naught. This is equal to 1. Okay. So the funda is whatever. You need to see what is happening. So let's say you have a certain filter. You want it to transform to another kind of filter. You just need to make sure that this variable S is replaced such that whatever is happening, so whatever characteristic you have in the current filter, the same characteristic shift to some other frequency wherever you want. For example, here, whatever was happening at 0, I wanted it to shift to whatever is happening. I wanted it to shift to infinity, right? So to do that, I just need to do the reciprocal of this thing. Same thing will happen if I wanted to convert a high pass into low pass. Now what happens if I want to do it for the band pass case? So for band pass case, what I needed at omega equal to 0, I want 0. At omega equal to infinity, I want 0. And at omega equal to some omega naught, I want 1. Okay. So what I will replace this by? So what was my low pass transfer function? This was 1 upon 1 plus S by omega naught. So what variable I can replace this S by omega naught as, so that I get these characteristics from the same filter. So if I replace it by, so S by omega naught, if I replace by S minus omega naught by S, I will get the, let's see if I get whatever I want or not. So what we have now is 1 upon 1 plus S minus omega naught by S. So this thing becomes equal to S upon S 2S plus 2S minus omega naught. Correct? So when this is equal to 0, just a minute, it's not this thing. So Mm, so we want a j over here so that at s equal to j omega naught, we get this as 0. And at s equal to 0, we want this term to go to infinity. And that is happening in this. At s equal to infinity also, we want this term to go to 0, this term to go to infinity, and that can be made sure by so if I have over here s plus j omega naught. No, wait. This times s plus j omega naught. So what happens now? So at so if s is equal to j omega, so we will have j omega minus j omega naught times j omega plus j omega naught divided by j omega. So at omega equal to 0, we will have this as so let's call this term as some s alpha. So omega equal to 0, we have s alpha as s alpha tending to infinity. At omega equal to infinity, we again have s alpha tending to infinity. Why? Because there is one omega over here, and in the numerator we will have omega square. So omega square by omega is equal to omega. So it again tends to infinity. And at omega equal to omega naught, we have s alpha going to 0. So if we replace this s by this particular s alpha, so s by omega naught by s alpha, we will get a band pass response. So HBP will be equal to 1 plus j omega minus j omega naught times j omega plus j omega naught divided by j omega. So let's try to expand this. It becomes j omega divided by j omega plus, so this can be written as, let's write it in form of s only for now.
Sir, can it be s by 1 plus s square by omega naught?
Sorry, s by 1 plus s square
By
by
omega.
omega naught. Yeah, that also can give you the wait, s by 1 plus s square by omega naught. Omega naught square, you mean? Not
Omega, omega naught.
so you need dimensionally correct terms, right?
Omega naught square.
Yeah. So here also it will be omega naught. Here also omega naught. So okay, we will try both of them and see. So let's call this S alpha 1. Let's call this as S alpha 2. So first of all, let's evaluate this, and then we will evaluate the other term also. So what we have, S upon S plus S square plus omega naught square. Okay. So this is actually, so this is band pass only, right? So at very low frequencies, it will be 0. At S equal to omega naught, at s equal to omega naught, again this this term will become 0 and S by S will be equal to 1. H band pass will be equal to 1, and at S tending to infinity, S square will go to infinity square, so H band pass will become 0 again. Okay, so replacing S by omega naught with S minus j omega naught times S plus j omega naught divided by S, this can be done. So the other term that we were saying is, what did you want? What was the other term that you were asking? S by
omega naught, s by omega naught by
S
1
by omega naught by
1 plus s square by omega naught square. 1 plus 1 plus
1 1 plus S square by
omega naught.
omega naught square. So here, okay, if we replace S by j omega, we get j omega by omega naught divided by 1 minus my omega square by omega naught square, right? So let's evaluate. At omega equal to 0, this term becomes 0. At omega equal to infinity, this term again becomes 0. At omega equal to omega naught, this term becomes infinity.
So it may be 1 minus s square by omega naught square. If I type like
Sorry.
that, it will work. 1 minus s square by omega naught.
So 1 minus S square by omega naught square. So even here also,
It will become 1 plus omega by omega naught square.
1 plus omega square by omega naught square. But what you wanted at omega equal to omega naught, you wanted this term to be
1.
no, this term shouldn't have been 1. So see, what was our original thing? At at S equal to, so this term had to be 0, correct? You want whatever you are replacing with at omega equal to omega naught, this should be 0, but this is not becoming 0. This is becoming some 1 by 2. So this won't work.
So how to assume that one, sir?
So you need to see, okay, so what we did over here. So we had this low pass case as 1 plus S by omega naught, and having S equal to j omega, omega equal to 0, S becomes 0. Omega and HLP becomes 1. Omega equal to infinity, S becomes infinity, and HLP becomes 0.
0, 0.
Right? We wanted to replace S by some particular S alpha, so that at omega equal to 0, S alpha becomes infinity, such that our band pass filter becomes 0. At omega equal to infinity also, S alpha shall remain infinity, such that our band pass filter still remains 0. Okay. And at omega equal to omega naught, our S alpha shall become 0, such that our band pass filter becomes 1. Okay. So to satisfy this, we need to find some S alpha of this form, right? So this can be done by, so S alpha is equal to some j omega, right? So j omega minus omega naught times j omega plus omega naught divided by j omega. So this is equal to S alpha. Now at omega equal to 0, this denominator becomes 0. So S alpha becomes infinity. Correct. At omega equal to infinity, the numerator becomes infinity square. So S alpha becomes infinity. At omega equal to omega naught, this term becomes 0. So S alpha becomes 0. So we need to replace S by this particular term. Now, if we scale this by some factor, or so let's say we scale this by some alpha and we scale this by some beta. Based on that, we can increase or decrease the sharpness of the bandpass filter that we want. Okay. So these two factors, alpha and beta, if we change these two things, we can, so around this omega naught, it will always remain 1. At DC, it will remain 0. At infinity, it will remain 0. But as we increase or decrease this alpha, it will behave, its quality factor will increase or its quality factor will reduce. But these three characteristics should always be maintained, which will be maintained irrespective of what alpha and beta you choose. Any other doubt? Is it clear now?
Yes, sir. Sir, which textbook we can refer for this filter transform?
A textbook. Okay, I will have to look at it. I think Razavi won't have these kind of transforms or something. Any textbook on control systems, I think, should have this. I will refer and get back to which textbook particularly you should refer to. I will have to look it up, but I think some control system textbook might have this.
Oh, just post
I
in
will,
the
yeah, yeah. Tell me.
forum. You can post in our forums.
Yeah, yeah, I will post in the forum. Or in the next tutorial, I can mention this. Yeah. Or do one thing. You know my mail ID, right? You mail me, and on that I will reply you back.
Is your mail in the forum, sir?
Um, I'm not sure. I will just type my mail ID over here.
Uh, it is best. It is good. It will be helpful.
So I've typed my mail ID here. You can mail me once on this mail ID. I'll reply you back on this. Any other doubts?
In our final exam, will the questions will be covered from every topic which was covered in our video lectures, sir? Is it be like that? Or?
Yeah. So whatever is covered in the video lectures on those topics will be covered.
Sir, assignment 4 question.
Yeah. Tell me.
Sir, assignment 4 6 questions, sir. Could you please explain?
Can you please repeat or type the question? Your voice broke in the middle. Can you speak again?
Sir, assignment 4 6. Could you please explain question?
Which question?
Sixth question. Yeah.
Sixth question.
So
Okay. Can you do one thing? Can you share a screen and present that question so that I can take a screenshot and then explain?
sir, am I sharing?
Yeah, it's coming up. I think it has gone again. Please share it once again, or I think it's there. You are just showing. Have you presented your entire screen or only a window? I think you have only presented the window, so I can only see the window over here.
Sir, it is only, is it only S-mail, sir? Your mail ID? S-mail.
Yeah, at smail.iitm.ac.in.
Oh,
Ravi, are you trying to share a screen?
Sir,
or
I
he
am
can,
doing.
or he can post in the chat.
Hello, sir.
Yeah, yeah, I can hear you. Uh, okay, so I think he is not here. Which current actually we are talking about, Naveen? Can you please elaborate? So are you talking dynamic scale circuit? Okay, let me. This one over here, is it? So this is I1. This current you are talking about, is it? The other circuit. This one. You can unmute yourself and speak. I think that will be more clear. In this circuit you are talking about?
No, sir. Just below one circuit. Just below this. Just now you showed me.
This one.
Uh, Below that, sir. One small circuit you written.
Just a minute. This one, is it?
No, sir. No, sir. Only small one, sir.
Wait, which one you are talking about? Let me scroll.
Sir, you started with this question only, sir.
Yeah, I started with this only. Which circuit you are talking about? This one, is it?
Yes, sir. Yes, sir.
Yeah. So I1 will won't go into op amp. I1 will go through this feedback impedance, and what voltage will we get over here is I1 times Z times. So if let's say this was only ZF and ZL, so
Sir,
voltage
but
at this, yeah.
I1 will not go to ZF, no, sir. Only the output current will come to that node.
No,
Uh,
I1 will go into ZF only, right? I1 can't go inside the op amp. So
Not
if
that, sir. I1 goes to that node, and after that, the output current will go to ZF.
uh, see, I1 will flow through this ZF, and so what will be the voltage at this node?
V0.
No. If this is virtual ground, right? If this is virtual ground and I1 flows through this impedance ZF, what is the voltage at this node?
IF into ZF. I1 into
I1
ZF.
into ZF. Okay. Now, if I want to increase this voltage at this node by A times, and I don't want to change this I1, what will I have to do? I will have to increase this impedance by A, right? So if I increase the impedance by A, my voltage at this node becomes A times I1 times ZF. Is it clear till this point?
Sir, how increasing the impedance gets that value increases the voltage?
So voltage time current, current times
I times ZF,
impedance.
like I1 into ZF.
Yeah, so I1 into ZF was the initial voltage. If I made the ZF, if I replace ZF by A times ZF, what will be the voltage at this node now? If I1 hasn't changed. Naveen, can you hear me?
Screen is not visible to me, sir.
Uh, your screen, my screen, I think my screen is visible.
Screen, the screen is not sharing to me.
Can anyone confirm? I think I have shared my screen. Ravi, can you read? Can anyone confirm my screen is visible, right?
Sir, screen is visible, sir.
Okay.
Yeah.
So,
Please. Yeah.
so yeah, I will just explain this dynamic range scaling concept once more. So what I want to, so this is an op amp in a large circuit, and I want that this op amp's output should increase by a factor of A without changing any other node in the circuit. So what I will do, and if any other node in the circuit is not changed, that means to say whatever current is coming as I1 over here and whatever current is flowing out of this node as I2 should also not have changed. Okay. So if I1 has not changed and I want the voltage over here to increase by a factor of A, in that case, I will make this particular impedance if I make this impedance scale by a factor of A, earlier the impedance time current was I times ZF. Now the impedance times current is I1 times A times ZF. So this voltage becomes I1 A times I1 times ZF. Now, if this voltage has increased and I don't want this current I2 to change, so I will have to increase the volt. And I2 is this particular voltage divided by ZL, divided by whatever impedance is there at this node. So I will have to increase this impedance also by A times ZL. So doing so, I can increase the voltage at this node without actually changing the transfer functions of other nodes. This is the principle of dynamic scaling. So can you please again, Naveen, are you able to understand this, or do you want some other explanation?
Yes, sir. But in writing the equation for non-inverting amplifier, sir, you will write KCL at that node. Only the incoming current I1 and the outcoming out current or I out will be coming through ZF. Like that we will write now, sir.
No, this output, what is I out?
KCL.
There is no I out in this.
Only at that node we will take KCL and we will write now, sir, in a non-inverting amplifier.
At which node?
So at non-inverting node, sir.
At inverting node, you mean? At this?
Yeah, inverting node, yes, sir.
Yeah,
Inverting node.
yeah.
So we will take KCL and we will write incoming current I1 and from output current I out will be coming through that ZF. Like that we will take and we will write minus RF by R1. Now you
Uh,
are telling I1 will flow through ZF.
Yeah, what is the output current? There is no output current. There is this current I1 that goes through this particular ZF. Okay, I will explain it through inverting amplifier only if you want. So let's say this is R,
Yes, sir.
this is V, and this is RF. Okay, so I1 over here is VI by R, right? Now this I1 will flow only through this feedback resistance, right? No current can flow inside the inverting terminal of the op amp, right?
Yes, sir.
Okay, so if this current I1 flows through this RF, what will be the voltage at the output? This voltage is zero. The potential
I1 into
developed
Z.
is RF times I1, right?
Yes, sir.
Okay, so this will become minus RF times I1. And what was I1? VI by R. So minus RF by R times VI. So where is I out in this?
Sir explained like that only, sir, in applying KVL at that node so that the output current will flow through this
No,
RF.
see, in this case, the I1 will be equal to output current. But let's say there was some load over here also, RL, let's say. In that
Okay, sir.
case, this won't be equal, this output current won't be equal to I1. There will be this output, this I1 will be there, and whatever V out by RL will be flowing, that current will also be there. So whatever you are saying will only be correct if there is no load at the output.
Oh, here load is there, so I1 will be flowing through the RF.
I1 will always flow through RF. In this case also only I1 is flowing through RF. But that I1 is equal, it so happens that that I1 is equal to I out because there is no other current flowing through this op amp. So that's why sir explained that an output current of so let's say here V out was there, and output current V out by RF will flow, and that output current will be the output current of op amp. But if there is some load at this node, then this output current won't be equal to only let's say V out by ZF. It will be V out by ZF plus V out by ZL. So that's it. The output current of the op amp won't always be equal to the feedback current that is flowing through that resistor.
But I1 also flows through the RF. Output current also flows through the RF.
No, no. See, output current's part will flow through RF. Here, I1 flows through this ZF, right?
Yes, sir. Yes, sir.
Let's say this I out is there. Now, this I out will divide itself between this ZF and this ZL, right?
Yes, sir. Yes.
Okay. But since we have already established that the current that is flowing through the, so if the current flowing in this direction is I1, the current flowing in this direction is minus I1. That's it.
Yes, sir.
No other current can flow, no other component of I out can flow in this direction. Why? Because if some other current flows in this direction, then KCL at this particular node will be violated.
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Any other doubt? Okay, so if there is no other doubt, that was it from today's session, and thank you for attending.
Thanks.